Dear colleagues and friends, ladies and gentlemen, I will present you the overview of some new results and insights related to solving the problem of hydrogen embrittlement mechanisms in metallic material. This presentation is a work of group of researchers from various countries. Pokazivač ne? Aha. Several institutions are involved in this research. We have a group of researchers from Serbia, which are working for more than 15 years on solving the hydrogen embrittlement mechanisms problem in metallic materials, but also we have two universities from the United States, University of Toledo, Drexel University, also recently University from Austria, from Brazil, and also our bilateral agreement with China. So we have partners from Institute for Advanced Materials and Technology, Beijing, University of Science and Technology, Beijing. So HELP plus HEDE model is the main topic, and we will talk about synergy of mechanisms of hydrogen embrittlement in metallic materials. Presentation content, briefly about problem. Then I will present the initial HELP plus HEDE model proposed by a group of researchers from Serbia in 2014 and 15. And then I will present the new results regarding confirmation, experiments, and models of so-called unified HELP plus HEDE model. And then finally some conclusions. Here is the overview from our review paper for 2019 about what should be done and what's the problem related to hydrogen materials interaction, generally speaking. We have four topics. One is phenomenology of hydrogen-related degradation, which is extremely complex topic. The other problem, particularly related to hydrogen new technology and transportation of hydrogen mixture with gases or pure hydrogen in pre-existing pipelines, is hydrogen entry and source, how hydrogen enter into material. And finally, what is the missing right now is a structure integrity model and predictive maintenance model to check how will materials behave under hydrogen embrittlement. And we proposed in 2015 structure integrity model based on multiple active hydrogen embrittlement macro mechanisms based on measuring and following the change of hydrogen concentration in material based on critical hydrogen concentration. And we are still working on so-called unified predictive structure integrity model for prediction of behavior of material exposed to various hydrogen damage mechanisms. Hydrogen is an old topic. In 1875, hydrogen reduced the ductility, Dr. Johnson, famous paper. Then we have in 2014 paper by Professor Robertson from US, which pointed out that several mechanisms of hydrogen embrittlement operate simultaneously. And then we proposed the HELP plus HEDE model as one of the options for synergy. So we can say nowadays that the synergistic interplay of various plasticity-mediated hydrogen embrittlement mechanism, including HELP and decohesion mechanism HEDE, are confirmed by numerous experimental evidence and through simulation and modeling. So we have two models for the synergy, and here is the difference. HELP plus HEDE model proposed in 2014 and 15 pointed out that multiple plasticity enhanced hydrogen embrittlement mechanism HELP, but also others, there are various mechanisms, together with the decohesion mechanism, are responsible for hydrogen embrittlement in steel. And recently it is confirmed that this model is applicable to almost all metallic materials. That is the difference between so-called HELP-mediated decohesion model proposed by a group from Urbana campaign, Professor Robertson and Sofronis, which pointed out that initial activity of some of plasticity-mediated mechanism, particularly HELP, is a prerequisite for eventual activation of decohesion as a final failure mechanism. And we show that it's not always the case, particularly at a very high concentration, higher than the critical hydrogen concentration. So overview about HELP HEDE model is a comprehensive concept on which several teams, as I presented, now work worldwide to confirm as a unified theory about hydrogen embrittlement in metallic materials. So HELP and other plasticity mechanisms together with HEDE synergistically are operative. And this HELP HEDE model is based on very carefully microstructural mapping of dominant hydrogen embrittlement mechanism depending on hydrogen concentration, microstructural characteristics of material, and stress strain state of the material in order to reveal the various hydrogen-assisted fracture modes after failure. So overview of HELP HEDE model, it is confirmed in iron, in almost all types of steel, including low carbon steel, high strength steel, martensitic steels, pipeline steel, but recently it is also applied and confirmed that it's operative in nickel-based alloy, aluminum alloy, and high entropy alloy, and additively manufacturing alloy. So I will give you some new results. Here is the original paper from 2015 in which we proposed the HELP HEDE model. We can see that we have a transition between mechanisms and the drop of mechanical property, which means particularly ductility happens not due to hydrogen-enhanced plasticity mechanisms, but due to activation and predominance of HEDE mechanism, decohesion mechanism. So we have a HELP dominant regime and we have a HEDE dominant regime, and which is interesting, the fracture features of low ductility sample and relatively good ductility sample is very similar. So we have activity of both mechanism manifested by microvoid coalescence, ductile mechanism due to predominance HELP and other plasticity-mediated mechanism. And then after accumulation, and then we propose the local HEDE micro concept, which tell us that we have, when we have accumulation of large enough decohesion incidence, you see we still have a remaining ductility in material, but we have a predominance of transgranular failed area, and after that intergranular, we have a very sharp drop in mechanical property, which means a drop in ductility, which finally provoked the hydrogen-assisted crack initiation and propagation, and that's the basis of HELP HEDE model. So here is the overview transition. HEDE dominance, HELP dominance, and we are working on mapping of conditions for activation, predominance of particular mechanism of hydrogen embrittlement depending on the microstructure characteristic, global and local hydrogen concentration, and stress strain level. Here is the overview of recent paper. You see we have 13 papers published between 2019 and 2024. And I will give you some new insights. We have two papers which are in press, in advanced materials, and also another in preparation and in press in International Journal of Hydrogen Energy. The other 11 are already published. You see there is a group of international researchers, Serbian group, work with several institutions worldwide speaking. And we will talk about the HELP HEDE model. I will present two new concepts, local HEDE microincident concept proposed in 2019, and totally fresh and new HEDE prone concept, which talk about the transition between mechanisms. So here is the overview about critical hydrogen concentration, HEDE dominance, and HELP mediated HEDE, and other plasticity-mediated mechanism. As you can see, we can divide, depending on the global hydrogen concentration, the behavior of material into two categories. We have so-called plasticity-mediated fracture modes due to effects of hydrogen, and the other side, we have pure embrittlement of material, which means that we have decohesion control fracture mode, in which case, which is very interesting and very enigmatic to understand, hydrogen promotes the plasticity of steel and other materials at low hydrogen concentration, so they increase the plasticity of metal. And after that, then sharply decrease And that transition is more important. So in the case of heat predominance, we have so-called hydrogen impeded plasticity of material, and we must carefully investigate when that happened in our material. So here is the microincident concept, which tell us, proposed in 2021 with a group of researchers from Australia and Serbia, that we have, even at a low critical hydrogen concentration, localized decohesion phenomena on the microscopic level. It's so-called HEDE microincident concept. And in the case of activity of HELP mechanism and other plasticity mechanism, we have so-called non-HELP mediated HEDE, which means that we have a full predominance of decohesion mechanism after accumulation of the large enough local micro HEDE incidence. And in that case, we have a HEDE dominance. So we have a both plasticity mediated fracture and also have a local intergranular and transgranular brittle failure due to HEDE mechanism. So they operate simultaneously. After that, here is the overview about local HEDE microincidence, which means that we have initiation of HEDE mechanism even in the case of relatively low hydrogen concentration into material, and after accumulation of large enough that HEDE microincidence, we have, microscopically speaking, the transition between ductile behavior of material to pure embrittlement, which means that we have a sharp drop of ductility of material after accumulation of that mechanism. But this is a continuous process, and we must map and investigate when HELP and other plasticity mediated mechanisms are predominant and when we have a transition to decohesion HEDE mechanism. I don't have a time to explain HELP and HEDE model mechanisms, but it's very well known in the literature. So here is the overview that very similar fracture appearance we have in low carbon steel, in nickel-based superalloy, and in aluminum alloy. As you can see, we have a transition between mechanism manifested by typical ductile failure, then combination of ductile brittle behavior of material, and then transition to full brittle behavior of material manifested by intergranular and transgranular cracks, which is a true confirmation of HEDE dominance and accumulation of large enough HEDE microincidence, which we have at a relatively low hydrogen concentration. HEDE-prone traps talk us about what is the position in microstructure which are prone to decohesion. So here is the list of location. As you can see, various precipitates, phase boundary, interface boundary, secondary phases, slip planes, ground grain boundary, pre-existing cracks are HEDE-prone traps. So when we have metallurgical engineering of material, we must carefully engineer materials to provide that we have a high strength by precipitation, hardening, and other mechanisms, but not to introduce dangerous hydrogen embrittlement prone traps where the decohesion phenomena will appear. So we proposed in our recent paper from 2024 with Chinese author a design of hydrogen embrittlement resistant alloy based on carefully engineering of twin boundaries, participates, and repeat boundaries metallurgical design in order to provide that precipitation are particularly good ones, semi-coherent with the matrix. So we must carefully, and on the other slide we will see how the high strength high entropy alloys precipitating hardening are very prone to hydrogen embrittlement because this schematic is not involved during the design of that particular alloy. This is the structure integrity model. I don't have a time to talk about that, about the transition from 2016 publishing Corrosion Journal. As you can see, we have a transition of mechanisms, and we have a analysis of critical hydrogen concentration and particularly prone part of microstructure. This is the brand new results. As you can see, we investigate the novel precipitation strengthening high entropy alloy, which have L 1,2 precipitates and ground boundary, which is also typical for steels and nickel-based alloy, and provide a very good ductility and very good strength of this high entropy alloy. But as you can see, we have a very high susceptibility to hydrogen embrittlement. We have a ductility drop here after hydrogenation in this slide. And as you can see, we have a decohesion and activation of heat mechanism on the grain boundary, which are strengthening by these precipitates. So this particular participation strengthening the high entropy alloy are very prone to hydrogen embrittlement due to existence of heat-prone precipitates and location in microstructures. You must carefully provide the metallurgical engineering of high hydrogen embrittlement resistance alloy. And we show how to do that in nickel-based alloy. Here is, again, work with a group from China and Serbia. As you can see, we provide a very high resistance of nickel-based alloy. Nickel-based alloy are typically very prone to hydrogen embrittlement. We provide the explanation based on HELP HEDE unified model, what's happening in this material. But what's very interesting that we introduce deformation twins and microbands into the microstructure of novel nickel-based alloy, which, as you can see, provides a combination of decohesion and microalloys. Microalloys means that we have remaining ductility of our material. So we are in the part where we don't have a heat dominance, so we shift from conventional nickel-based alloy to novel-based alloy, the active mechanisms below the critical hydrogen concentration. We provide a detailed analysis, as you can see here, in comparison to Inconel 718 and Inconel 725. There's a conventional nickel-based alloy as well as other nickel-based alloy. The degree of hydrogen embrittlement susceptibility of this novel alloy developed in China is much lower, and this nickel-based alloy provides very high hydrogen embrittlement resistance. That's the direct approach and confirmation of microheat incidence and HEDE-prone concept, which I previously explained to you. One slide more in order to confirm that mechanisms, together with Professor Bassaran from the University of Buffalo and the colleague from China, we provide a very comprehensive paper which was published in 2013, in which we tried using unified mechanics theory, which is entropy-based ab initio method, to confirm the validity of HELP HEDE model on physics level, on fundamental level. And we have some very promising results. We implemented the HELP HEDE model and transition between mechanisms in a case of high cycle fatigue of pre-hydrogen brittle material, and confirmed that due to HELP HEDE activity, we have a shortening of fatigue life, as you can see here on the diagram. So the simultaneous spread with the number of cycles fatigue curve due to HELP HEDE activity, a different hydrogen concentration confirmed that when we increase the hydrogen concentration, we have a much larger increase in entropy because of heat mechanism, and the lowering of entropy due to HELP mechanism, which is a direct confirmation of HELP HEDE model on ab initio level. Professor Bassaran working for more than 30 years on unified mechanics theory. So, some of the conclusions. I try my best to give you an overview. It's a very complex topic, and I'm aware that it's not easy to present the results, but what's important, it's important that we still don't have some results which will finally confirm about hydrogen embrittlement mechanism. We need the microstructure mapping techniques, atomic tomography, and other techniques. We also published a paper with the authors from Brazil and Austria, in which we pointed out, in order to solve the problem of hydrogen embrittlement, we need to confirm these hypotheses of mechanisms, because all these mechanisms, HELP, HEDE, are well known but still not confirmed on what type of level. To see that when you have a high hydrogen concentration, which means that you need to map the hydrogen distribution into microstructure, and then to measure the local hydrogen concentration and show that we have high hydrogen concentration, medium, and local. There is a big problem how to do that. But a novel microstructure depending local heat micro incidence and heat prone concept within the unified HELP HEDE model represent the framework for hydrogen mechanism mapping and further investigation of their synergy and defining what is very important, the precondition for the transition between them, which means when we can safely use some components exposed to hydrogen embrittlement and when it will brittle fail due to heat predominance. So, you know, brittle failure, hydrogen embrittlement is a typical brittle failure which happens immediately and it's very dangerous. Thank you very much for that.